Okay, let's go ahead and get started. We were in substitutions, nucleophilic substitution. We went over SN2 pretty well on Tuesday. Let's continue with SN1. So in SN1, we have our substrate with our leaving group. The first step is that the leaving group leaves. Okay, and we had a discussion on Tuesday about why that happens. Again, those molecules, those bonds can be stretching at any one time. That could be broken. The more stable these two species are, the more likelihood you'll go from what is the single bond to this, for lack of a better term, zwitterion, these two different ions. But that's just possible. The more energy I put into the system, the more likelihood that is. Remember that a bond is just like a spring. So if I can get that spring to really start to shake, there's a chance that I'll break that spring for a little while even. So then the nucleophile, so leaving group leaves with its electrons, leaving a carbocation. Then the nucleophile comes in. For simplicity case, we'll call this a negative nucleophile. That thing gives us the new product. So we have a two-step process. The first step, goes over a high energy transition state, and then we have a low transition state. And we've had questions about why this first one is bigger than the second. We think about that loss of the leaving group going to the carbocation is going to be a high energy species, right? So that's rate determining step is here. But then the nucleophile attacking an empty carbocation, right, an empty orbital, is going to be relatively fast, right? All we're really worrying about here is getting them in close proximity. Right? Now, this first step can be reversible, right? And the second step potentially could be reversible depending on what's going on and what that nucleophile is. But that second step is going to be much faster because I've already got the positive charge. Now I'm having the positive charge, the non-octet rule empty orbital reacting with another negative. Okay. Again, this is where we get the SN1, so it's substitution. Nucleophilic. Okay, first order or mononuclear. The rate, because of that rate determining step, is just going to be the substrate. So it's only the rate of reaction here, unlike SN2, is only the concentration of my substrate. The second step where my nucleophile is a fast step. I can increase the concentration of the nucleophile, but I'm not going to increase the rate of the reaction. That doesn't mean that increasing the concentration doesn't increase the likelihood of the reaction. It just means it has no impact on the rate of the reaction. Okay. It's a subtle difference. One has to do with speed. The other one has to do with the probability that it's going to occur. So by changing the concentration of my nucleophile, I can increase, if we think about up here, right, I can increase the amount of nucleophile in solution versus the amount of the leaving group in solution. That can impact the probability that the nucleophile will substitute for the leaving group, but that doesn't change the rate of the reaction. So if we think about our different things we can look at, when we look at our substrate, what we really need for the substrate is the stability of that carbocation. So if we think about the possible carbocations, we think about the different stability of carbocations. If we look at these, the tertiary is going to be the most stable because of something called hyperconjugation. So if I have my positive charge, got that empty orbital, and I have a carbon next to it with my hydrogen attached, I can have back donation of electron density from the sp3 orbital, or the sp3s bonding orbital, to the p orbital. So this is called hyperconjugation. We can think about it somewhat like inductive, right? And we did use this when we were talking about the stability of bases, right? That a halide would put pulling electron density, but a methyl group could contribute electron density. Part of that is that if we have this type of positive charge with a p orbital, we can get back donation of electron density to that positive charge. If we have more carbons that can hyperconjugate, then we have more possibility of hyperconjugation, right? So when we look at this here, right, this is the most stable carbocation, right? And this is the least stable. There's no hyperconjugation occurring in the methyl. Then we have one methyl here, and then we have two methyls there that can give us hyperconjugation. So the stability of the carbocation is going to be tertiary over secondary over primary. Which means if we're thinking about SN1, that stability of the carbocation is going to be very important. So therefore, in an SN1 reaction, you know, our substrate, it's the tertiary carbon is going to be faster than the secondary carbon, which is going to be much faster than the primary carbon, which is going to be excessively faster than the methyl. So in an SN1, right, it's the tertiary that is the most likely. And then by the time we get to primary, we really say it does not react because it's too slow to see what's going on. These are going to favor SN2. So what we have with substitutions, right, is our substrate, we have a difference in the way the substrates work. If it's a methyl or a primary, low steric hindrance, right, then that's going to go SN2. If it is tertiary or secondary, it's going to tend to go, if it's tertiary, it's going to tend to go SN1 because it's too sterically hindered to do an SN2, and it's a more stable carbocation. It's the secondaries that we have competition, right? A secondary carbocation could form, and a secondary carbon could have backside attack, right? So we think about this when we look at our substrates, methyl and primaries, that's pretty straightforward. It's going to be SN2. Tertiary, that's pretty straightforward. It's going to be SN1. It's the SN2s that are going to be a little bit different. The other thing we can have is stabilized carbocations. So if we have something like this, we can go to this carbocation, but this carbocation has a resonance structure. And because it has a resonance structure, it's going to be stabilized. So this is a secondary position, but it is a secondary stabilized position. Because of that, it's going to behave more like a tertiary as far as rate. And so that's going to have a tendency to be SN1. Now, that doesn't mean that all stabilized carbocations are SN1. If we take a primary position, that's also going to be stabilized. But since this is primary, right, that means that it has low steric hindrance for an SN2. And since this is stabilized, it's more likely an SN1. So here's a species where we have this competition. Now, if we think about this, if I have a really good nucleophile, which one is going to predominate? The SN2 is going to predominate. If I have a really weak nucleophile, which one is going to predominate? The SN1 would predominate. Okay. So the substrates can give us a big hint, but we have to look at everything that's involved. So for SN1, what drives the rate is going to be the stability of this carbocation. If that carbocation is not very stable, then this reaction is not going to proceed in a timely fashion. If that carbocation can be stabilized, either by being a tertiary from hyperconjugation, right, or from resonance, so being a stabilized carbocation, then that's going to favor an SN1 type process, or at least the rate for that is going to be timely. Questions about the substrates? If we think about nucleophiles in an SN1, SN2, we can use relatively poor nucleophiles. That's because the first step is the separation of the leaving group from the So first step is the bromide leaving. This is going to be a stabilized carbocation. This is the same substrate we looked up at the example. The nice thing about this substrate is what? When I do the resonance, do I get two different resonance structures? Well, you get two different resonance structures. Do they appear different? No, the carbocation is still on the second carbon. So this attack at this carbon and attack at that carbon actually give you exactly the same molecule. Okay. So this is a nice stabilized because I only end up with one potential carbocation substrate. Now, if you name that Bob and that Mary, you'd have two, but once the reaction is done, you won't be able to tell the difference between Bob and Mary. Now, if we think about the next step, which is the nucleophile, does it matter once we get to the carbocation whether this is a good nucleophile or a nucleophile? It really doesn't matter. All I need is a nucleophile. So once I have that carbocation, all I need is a nucleophile. So water has a lone pair, so it's a nucleophile, but it's not very basic. We don't think of those electrons being very available, right? So this is not one of those where we look at it and go, oh, this is really great nucleophile, like a hydroxide would be a good nucleophile, but water is a less good nucleophile. Amine is a very good nucleophile, water is less, right? So we don't have a really strong nucleophile, but it is a nucleophile. That's really all I need for an SN1, is something that has the available electron. Now, this reaction that I'm showing actually has a special name. Let's continue the mechanism here. So this can come in, right, attack that. That then results in either the front side, we talked about this a little bit on Tuesday. We'll look at it again in a second. Right. But now that's not my final product, right? My final product was the alcohol. So now what I need at the last step is and I'll just do it with one, is a proton transfer. And this is common. You'll have many reactions where you have to have a proton transfer to get the reaction started, or you need a proton transfer to get the reaction completed. And here, the only thing that we have for a proton transfer is water. So the water in this case is both the nucleophile and my proton transfer reagent. And proton transfer is just a fancy name for acid-base reaction. So the base is going to come and pull off the proton. To give me my product. This reaction is a special name. And if I could spell it, you could learn it. Okay, savolysis. Okay, if you break that named out in the Latin, lysis, breaking, solvent, solvent breaking. Because all I've done up here is taken the substrate, right, and added a solvent, a nucleophilic solvent, but a solvent, right? So we added a solvent that could be a nucleophile, and we end up with the alcohol. Water is the big one, right? Hydrolysis would be water. So if I take usually you add a little bit of heat in this. Often you add heat anytime you have an SN1 reaction. Why would you add heat? SN1 reaction takes more energy, right? I'm forming a carbocation. The more heat I have, the faster it's going to go, because I need to break that bond. I have to have a leaving group leave first. So this would be hydrolysis, right? Because I'm using water as my solvent. But I don't always have to use water. Take the same substrate. This time, let's use methanol. And instead of ending up with an alcohol, right, we end up with a ether. This doesn't have a special name. This would just be a solvolysis reaction. So since SN1s will react with poor nucleophiles, anything that is a nucleophile, then we can have this type of reaction, the solvolysis. Solvolysis reactions are SN1s. That's because remember when we talked about SN2s, I need a good nucleophile to get them started, right? So to get this process to occur with through an SN2, I'm going to have some type of nucleophile. So I'll have sodium hydroxide in water. The reactive species would be the hydroxide, that'd be the good nucleophile. The water would just continue to create that product. Here, the only reactant we have is the solvent. Right? Might need to add heat to get it to occur, but solvolysis is a special type. Okay, so we went through substrates. Tertiary is going to be favored over the rest. We can have stabilized carbocations. When we look at nucleophiles, any nucleophile will do. Okay, solvolysis is a special form of an SN1 type substitution. Let's look at leaving groups. We just need a good stable leaving group. So not much different than an SN2, right? We have to have a group that's pretty good. You will see in especially older books, some things like point charge. So if we looked at an SN1 leaving group, something that's small with localized electron density would favor an SN1. They don't put this in most modern books because there's a lot of exceptions to this. But if you think about it, if I'm going to go from a bonded species to a positive and negative, the more positive and negative the species is already, the more likely I'm going to go from the bonded to the non-bonded, right? So the SN1 leaving group of being a small point charge makes sense from the standpoint of I'm already close to being a positive and a negative. For SN2, leaving group, again, it has to be a good leaving group. Here they usually say, you know, larger, delocalized. If I spell delocalized right, that'd be helpful. So, you know, something like this, right, could be a slightly better SN2. Okay. Now, this is a very, very subtle difference. Okay. So it can be important to where the reaction goes, but it's of the things that you're going to do, what you need for a leaving group is a good stable leaving group, whether it's SN1 or SN2. We talked about stereochemistry a little bit on Tuesday. Let's talk about a little bit more for an SN1. And we'll use this example. So we start with a chiral species. What happens in that first step is I go to a carbocation. That carbocation is sp2 and is therefore planar. That means that whenever my nucleophile comes in, that nucleophile could have come from the top, or that nucleophile could have come from the bottom. And if the structure is simple like this one, there's not going to be a real difference between the top face and the bottom face. Especially in biological molecules, you have very complex structures. And one of those two faces could be blocked out, not by the carbocation, but by what else is around there. So you could have the carbocation here, you could have a substructure that's underneath that carbocation, which really blocks that other face, which means I'm only going to get attack at one side. Okay. But in simple molecules like this, they're in solution, they're going to be floating around. Both of those sides are going to be the same. And as we talked about on Tuesday, this gives us a racemic mixture. So we can have the alcohol going up, right, and the alcohol going down. So I'll have a 50-50 mixture of this. So this is known as racemic. So let's look at our two reactions here. So SN1, SN2, when we look at our substrate, remember methyl better than primary, not 10, primary, secondary, and that's driven by size and steric hindrance. For SN1, it's going to be tertiary, secondary, and stabilized secondaries. And that's going to be driven by the stability of the carbocation. For nucleophile, for the SN2, we want a good nucleophile. For SN1, we want any nucleophile. And so in SN2, the nucleophile has to actually initiate the reaction. It's attacked to the backside of that leaving group, right? Attacking the antibonding orbital of the sp3 bond is the important part to get the reaction started. In SN1, it's got a carbocation there that's unstable. It's going to attract anything that has a lone pair. So anything. Leaving groups are about the same. Right? We need a good leaving group. It favors polarizable leaving groups, right? Because what's happening in our transition state for SN2 is this negative coming in and the leaving group leaving all in the same transition state. So it's going to end up with partial negatives, partial positives. And so polarizable is the one we usually can refer to here. For SN1, needs a good leaving group, right? We need a good leaving group. And if we nuance it right, we want point charge. But a good leaving group is a good leaving group. Okay, we're not going to have a good leaving group that will say, oh, I'm an SN1 reaction, I'm not going to leave because it's SN1. No, it's still going to leave. You know, there's subtle nuance differences between our leaving groups, but again, they're subtle, not like our substrate, not like our nucleophile. When we look at stereochemistry, for SN2, we get inversion. So if it was the leaving group was on the front side, the nucleophile is going to come from the back side. So I'm going to invert that stereo center. For SN1, I'm going to get retention and inversion. In most terms, it's thought of as being racemic. Depending on your solvent, it could favor inversion over retention. So in some books, they spend a lot of time talking about the fact that inversion is favored over retention. If we think about this leaving group leaving, so I've shown it this way, right, with that bromine hanging out over here. But if this is in a solution that is not very polar, right, so let's say a less polar solution, will that bromide and that carbocation be solvated very well if it's in a non-polar solution? No, right? It needs a polar solution, right, to really start to stabilize, solvate those two cations, right? So if it's in a non-polar solution, what happens? The negative hangs out with the positive. And where is the negative going to hang out with the positive? Exactly wherever the negative came off, right? So if I don't have the ions being solvated, what happens is I break that bond, reform that bond, break that bond, reform that bond, right? Nothing's really moving. What that means is, although this goes to be a carbocation, right? So if that becomes a carbocation, this bromide could still be close to it, right? It's not floating away. Because it's close to it, if we think about it, where would the nucleophile want to come from? The side where the bromide is, or the opposite side? Well, it come from the opposite, right? My pinky on my hand here. Now, if I'm in a really good solvent, and SN1s like to have good solvents, what happens to the bromide? It gets solvated and floats away, and I have my carbocation that's also solvated, and now my nucleophile attacks either side it wants to, right? So there can be some subtle differences here. The takeaway of this is SN2 is only inversion. SN1 is inversion and retention. Now, it's not always an equal 150-50 mixture, right? But both are possible and both will occur, right? Sometimes in enzymatic solutions, you don't have both occurring, but that's because they're driven specifically by that biological system, okay? But in an open solution like this, retention inversion, whether it's 50-50 or 49-51 or 48-52, that depends on, that can be changed by my solvent that I choose to use, okay? So let's look at nucleophiles in more detail. Spelling's having trouble spelling this morning. Okay. In general, when we pull a proton off, that's going to make it a better nucleophile. In general, stronger bases are better nucleophiles. And next Tuesday, we'll start to get into elimination reactions. Okay. Stronger bases make better nucleophiles, but stronger bases also make what? Stronger bases, right? So when we get to eliminations, we'll also see that impact, that a stronger base. But if we think about water versus hydroxide, hydroxide is a stronger base. We can think about amine is going to be better than water. It's got more available electron density. The conjugate acid right? And again, just relevance here, but pKa should be around 10. pKa here is around 0. Right, so therefore, if we think about that, the nitrogen has more available electron density, pulling that proton or reacting with that group. It's got more electron density there. We also have some nucleophiles that you may not think about. So like nitrile, okay, usually shown as something like sodium cyanide. Right, this is a really good SN2 nucleophile, but it'll work on either. Why is it a good SN2 nucleophile? Well, that has to do with its structure. You think about it almost as an arrow, right? No steric hindrance here. I don't have to worry about any bulk. So that makes a good nucleophile. The other good nucleophile for SN2, but also SN1, although you mostly see it for SN2, is the acetate. Remember, this is a more acidic proton. We can pull that proton off. And again, it is a good SN2 style nucleophile because it's linear, right? There's not going to be a lot of steric hindrance to this. Sulfur nucleophiles are really good nucleophiles, whether that's the deprotonated, the flavoxide, or the hydrogen sulfide. Those are going to be good nucleophiles. Okay, and again, what we're looking at is the availability of electron density. Now, halides are good nucleophiles. Fluoride is a good nucleophile, but fluoride carbon chemistry is really unique. So you do see it in some places, but actually making carbon fluorine bonds is unique. In fact, it's a subset of organic chemistry, just specifically associated to carbon fluorine chemistry. So you don't see that one as often. So that's why you see iodine, bromine, and chlorine repeated over and over again. Now, these are all good nucleophiles, but they're also really great leaving groups, right? So this complicates it, but these are good nucleophiles. When we think about leading groups, right, again, our halides are good leading groups. Right, fluoride is over here on the side. Fluoride doesn't make a great leading group. That's, again, one of the reasons that fluoride is got special chemistry here. And it doesn't have to do with the fluoride not being stable. It has to do with the energy of the carbon fluoride bond. But you don't see fluoride being kicked off by other groups easily. One of the big innovations in chemistry in the last century was carbon fluoride Teflon. Okay. So if we think about Teflon, it's pretty impervious to all kinds of things. The Teflon that we use in cooking was necessary for the reactions and the gaskets and things in the space uh, conquest. You had to have rubbers that wouldn't burn up. But the problem with rubbers is rubbers will react with oxygen and burn up. And so as you got a lot of heat, you needed something that could withstand the heat of reentry as well as the heat of taking off and not burning up as you started to get the oxygen. And so what they started to do is fluorinate the polymers to make the rubbers. So they had fluorinated, not just Teflon, right? But other species. That was a big area of chemistry for a while, was coming up with high energy fluorinated polymers that could be used for high energy gaskets and things. Even things like potential fracking takes a lot of pressure at high heat. And that also, when you're drilling, you've got to have a gasket that withstand the heat. And so fluorinated. So when we think about leaving groups, we have those. So anything that's, kind of a stable anion is a good leaving group. What's not a good leaving group is something like a hydroxide. No. Nitrogen negative and carbon negative. So you never see that, right? You don't see a carbon-carbon bond being broken as a leaving group. But it could be, you could think that you might want to take this molecule and turn it into this molecule. Right? But the problem with this is that the reaction here, right? I want to go forward, but if we think about it, the bromide coming in and displacing the hydroxide gives me this, but the back reaction, right, is a favored reaction. So sometimes what we have to do is start with a certain group and modify the leaving group. So hydroxide is a bad leaving group, but there's lots of alcohols, especially in biological systems, right? Lots of OH groups. And we might want those OH groups to react. So what we need to do is modify that group. There's a couple of ways to do that. The first is to protonate that group. So we can make that a better leaving group by modifying it, right? So first thing we do is we protonate, we do a proton transfer, acid-base reaction. Now what's my leaving group? Not the hydroxide, but water. Water is a great leaving group. It's very stable. So now the nucleophile can come in and I'm showing this as an SN2. We'll talk about that more when we actually get to that chapter, when we look at conversion alcohols to bromides. But what we're doing here is activating leaving group. We're actually changing the leaving group from hydroxide to a water. The other thing we can do is convert our hydroxide. So we can change the poor leaving group of the hydroxide into a good leaving group of this tosyl, this mesylate, this sulfonate ester. Questions about this one? The way we do this is react it with, and we'll look at this mechanism later. But we can take this mesylate and this mesyl chloride compound and turn it into the sulfonate. Then the sulfonate becomes a good leaving group. And so then the bromide will kick off the good leaving group. The other one you're going to see for sulfonate esters would be the tosylate. Couple of things whenever you're doing this, right? In this condition, right, we go from retention of stereochemistry. The reason that we have retention is the reaction is not occurring at the carbon, the reaction is occurring at the oxygen. So it's the oxygen lone pair that's important in the transformation to the tosylate. Also, this PY down here stands for pyridine. We looked at this one and there was some homework on it. Pyridine is a good base, right? And we refer to it as a proton sink. When we want to get rid of a proton in a reaction to get it to proceed forward, pyridine is a good one to use. It makes a stable acid. It kind of takes the proton away and doesn't react with anything. Now, both of these can be abbreviated. So the mesylate, this can be known as just the MES. Tosylate is just known as TS. The TS chloride. This one is the one you're going to see quite a bit, tosylate. It's easy to work with. You'll see it as a activating agent. So when you're looking at leaving groups, if it's something that can be stable as it leaves, then we're good to go. If not, then we might have to activate something to become a good leaving group. For alcohols, that's the one that we're going to be looking at most often. The way to activate those is to either react it with an acid to protonate it, or to convert it to a sulfonate ester, such as the mesylate or the tosylate. Questions about leaving groups? Trying to remember where I wanted to go from here. Now, to predict the products of a reaction, we need to be able to consider what kind of mechanism is going on. It's going to be important to determine, in some cases, their stereochemistry. So if we look at a species like this, right, and we add in water, the question is here is, do we have only inversion, or do we have a mixture? Right, and that little wiggly line there means it's either backwards or forward. So if it is SN2, right, then we're only going to get inversion. But if it is an SN1 mechanism, then we're going to get a mixture. So in this case, what we need to line up, right, is what is our conditions, right? And like with ARIO, we need to think about what the priorities are going to be. Okay. And one of the things, if you think about what we said about leaving groups, right? Good leaving groups are good leaving groups. If we looked at nucleophiles, right, we need a good nucleophile or any nucleophile. But the one that really sticks out as our highest level is going to be the substrate, right? If it's a methyl, I'm not going to get any SN1. If it's a tertiary, I'm not going to get any SN2, right? So kind of like the ARIO that we use for acid strength and base strength, we can use the substrate as our primary. So in this case, I have a secondary substrate, right? So there's my secondary. Is that all I know about it? Does it have resonance? And again, sometimes what you have to do is just on the side of the paper, write out, okay, if that bromide left, I'd have this. Is that stabilized? Yes, that's stabilized. So this is not only secondary, it's a stabilized secondary. And stabilized secondary, right, could be SN1, right, because it makes a good stabilized, but is a secondary substrate eliminating SN2? SN1 looks plausible, right? That looks, but it's also possible that it is SN2. So what we need is another piece of evidence. And so we can go to our nucleophile. What kind of nucleophile do I have? Well, I've got water. Water is my nucleophile, right? Nothing else is shown in the reaction. Is water a good nucleophile? No, it's just a nucleophile. Right? It has the lone pair. So if we're looking at just that information we don't have anything else. Well, what about the leaving group? Is it a good leaving group? Yes, it's a good leaving group. Is a bromide going to obviously shift it one way or the other? No, it's got a good leaving group, right? So looking at this, what I have is I have something what is a good possible SN1, but hasn't eliminated an SN2, right? So first level, I'm kind of citing SN1, but I still have an SN2 in my back pocket. And then I look at my nucleophile. What's my nucleophile? It's a nucleophile. A nucleophile is going to favoring SN1. What would I want if it was SN2? I'd want a good nucleophile. So my best prediction here is that I'm going through an SN1 reaction. And I just remembered what I had forgotten. we need to talk about solvents. So the other part of the reaction that we can modify is our solvents. So let's look real quick about how our solvents react with SN1 and SN2. And for that, we need to look at the mechanism. So nucleophile attacks electrophile, leaving group leaves. And my transition state is this polarized partial negative, partial positive. When we look at SN1, I'm gonna go ahead and erase that. Our leaving group leaves, giving us a full positive and a full negative, right? And then my nucleophile comes in and attacks, right? But here is the reactive species, right? Here is the transition state. So if we think about different solvents, what kind of solvent do we want for an SN2? Well, we want a good solvent, right? It needs to solubilize everything. But do I form really positive or negative charges in the rate determining transition state? No. How about SN1? Yes, right? And it is very polar. In that rate determining intermediate, in this case, not transition state, but intermediate, I am forming full positives and full negative charges. So to stabilize that, it's going to be stabilized by polar solvent, and more so by protic solvent. So we have been talking about the substrate as if it was in a vacuum, but it's not in a vacuum. When we form that positive and that negative, there's going to be a solvent there. That solvent can do nothing or it can help. So if it is polar, it's going to help. And the one that'll help the most is protic. So now we need to look at our solvents and what does that mean? So for our solvents, we have polar and apolar, and we have protic and aprotic. So if we look at something like hexane, okay, that's our solvent, hexane, we use it, okay. Is it polar? No, not polar, right? And it's not apolar, it's nonpolar, sorry. My kids are learning Latin, so I'm starting to put A in front of everything. Nonpolar. And protic, aprotic, what do you think protic means? Available proton, right? It has available protons in it. Is there any available protons in hexane? Well, there's lots of hydrogens, but is a hydrogen carbon, is that hydrogen attached to a carbon available? Is it acidic? No. And so it's going to be aprotic. We can look at something like acetone. Acetone is polar, right? I have a dipole moment. It is polar. But again, I have no hydrogens attached to hydrogen bonding hydrogen. So therefore, it's going to be aprotic. But then if I go to something like methanol or ethanol here, right, it's polar. and it's protic. So alcohol type solvents are going to be protic, and they're going to be polar. And why that's important is that the carbocation, especially if there's a lone pair, right, can be stabilized by that lone pair. And the leaving group can be stabilized, right, by the proton. So non-polar aprotic solvents, right, are okay for SN2. Usually the problem with polar aprotic solvents is they won't dissolve good nucleophiles, because most good nucleophiles start as salts, like sodium hydroxide. It's a salt. I have to dissolve the sodium hydroxide before it starts. So SN2 prefers polar aprotic. Now, will it work in a polar protic? Yes. Right? But an SN1 favors a polar protic because it'll stabilize that carbocation. So by changing the solvent in SN2, I may make a small difference, but changing the solvent in SN1, I may make a huge difference. So if we go back up here to our reaction, right, one of the things we didn't have because I hadn't covered it yet is, what is my solvent? Well, my solvent, the only thing shown is water, right? And water is a polar protic. Okay, that favors SN1. So we're running low on time, and I want you let you out on time so you can take your test maybe before your next class if you want to, your quiz. So you need to be able to identify polar and apolar, polar and nonpolar, and protic and aprotic. For polar, nonpolar, does it have a dipole moment, right? Then it's going to be polar. If it is aprotic and protic, what you're looking for is a proton attached to a heteroatom such as oxygen, nitrogen, hydrogen bonding. So if it has hydrogen bonding, it's going to be a protic solvent. Protic solvents favor SN1 because it can stabilize the carbocations. It's not that it disfavors SN2. I can use a polar protic solvent for an SN2, but if everything is swinging SN1 and I have a polar protic solvent, then the reaction is set up for an SN1. Okay. All right. On Monday, we'll finish up this chapter and we'll start looking at eliminations. The Soda book's not great at elimination, so I'll add something in. The quiz, you got from 8:55 to 10:55 to finish it. 15 minutes once you start. Okay, good luck.